evening, good afternoon, good morning, and very good morning for those in Japan. Hi, NASA, good to have you with us. Yeah, so it's great to have people coming back for the third day of this workshop. We thought that perhaps not everyone would, so it's fantastic you did, just because this is the third day when we want all of you guys to begin to do some work. So yeah, so I will just put up my PowerPoint slide today, if I can remember how to do anything at all. I'm getting a bit stuck already. Is that the right PowerPoint? Yeah, okay.
That's why you have a glass of wine.
No, I'm trying to find. I think I got the wrong PowerPoint. Well, what I do is just hold on for a sec. I'll make sure I got the right one. Can you?
Yes, we see it. Okay,
tell me what
perfect.
PowerPoint you're seeing? Oh no, I think that is my old PowerPoint. I want. Sorry, that's not the right PowerPoint slides. I want that PowerPoint. Ruby-doo, just please, kind of talk amongst yourselves.
Well, what we can do is actually have by Charlie.
No, here it is. I got it now.
You got it.
No,
okay.
got it now.
Perfect.
Are you sure? I still
No,
see
that is still the old PowerPoint. So why don't you get?
So, Charlie, just go ahead and you give the housekeeping notes and in introduction into technologies.
So let's see if I can bring up my and do you see the slides?
Yes, perfect. Thank you.
Okay, great. All right. So hello, everyone. Welcome back to day 3. And I think by now everybody knows exactly what to expect. But for those who are joining for the first time today, some technical guidance. Please turn off your microphone unless you are speaking, presenting. For any technical assistance, please chat with Nico Caltabiano, who has been helping us throughout this journey. For question and answers and discussions, Etherpad remains our best friend for this workshop. We do have a day 3 Etherpad, so if anyone wants to bring up any questions or comments, please feel free to use it. And also the raise hand option to ask questions or share comments during the open discussion sessions that we have scheduled for today. And the rapporteurs are going to be providing their reports today. So, and then they are requested to be within the time limit. We are not implementing a timekeeping, but of course, we will give a little warning if it's going over time. So for the breakout groups, each breakout group discussion again happens in a separate breakout room on Zoom. Participants will be sent automatically to the breakout rooms depending on the bogs that you've signed up for. And bogs will last for approximately an hour, a little over an hour today. And a message to wrap up the discussions will be broadcast about 5 minutes before the end. And rapporteurs are again expected to summarize the discussions as a 5-minute presentation in the plenary. And so for today, the lineup in the 2 sessions that we have, the first session will begin with summary reports for the sessions that have occurred on day 1 and day 2. Laura Wilcox will summarize challenges of climate modeling. Chris Smith will summarize societal needs for climate information. Aiko Voigt will summarize science and technology. And Matthew Miselinsky, will summarize technology and accessibility. And following this summary of reports, we'll have a 20-minute discussion and then break. And then in the last, in the session 2, we'll have the breakout groups, the 4 breakout groups that are listed here. And we have the chairs and rapporteurs assigned to all of these breakout groups, and then lastly we'll have the plenary. So thank you again for all the volunteers for rapporteuring as well as for chairing these breakout group sessions. And so over to you, Piers.
Yeah, can you stop sharing? Cheers, sorry. Yeah, so, okay, so it is excellent to have everyone back with us again. I apologize, the technology didn't work first time. It obviously doesn't mix well with a glass of wine, but we're going to give it one more go now. So okay, so it's really important day today where we really begin to distill the diverse discussions we have had before, and we want to distill them into some key messages and ideas coming out. And we ought to bear in mind too what we want in the way of workshop outputs from our work today and tomorrow. So the first thing we want to try and develop from this little white paper produced by Wcrp that we will put out for consultation with the wider community, and this wants to come with some high-level recommendations. It could be big ticket idea that Wcrp might take on and coordinate, or something they might not do now. And we think about what it's capable of. So Wcrp can provide some direction, guidance, coordination, and facilitation for our kind of global community. And particularly important for this workshop is that Wcrp is just getting going with this ESMO, which is the system modeling and observation coordination core projects in developing. So we can really input to the beginning of that. And I think it's important as well to try and consider which other organizations that Wcrp might want to connect with and coordinate with. And so that is the kind of one key outline of what we're going to do today and tomorrow for the workshop. The other key thing we want to try and produce from this work is we want to have a peer review publication, and we obviously can't write that in one day, but we will hopefully, after today, Vaishali and I will try and put an outline together, and it would be good to really have some in-depth discussion of that when we come back tomorrow, as well as the Wcrp recommendation idea. Okay, so that's what we think we want to do from this workshop. And if you have a different opinion of what we should be doing, you can put that in the heater pad. It'd be good to have your thoughts on what we're trying to do. But with that, I'll pass back to Detlef, who is going to share the first round of things today. Back to you, Detlef.
Thank you, Piers. We are now 73 people online. I think the number still goes up, and by the way, the YouTube recording is actually very much used. Just to let you know, something like 300 people have already watched it. But we will start now with listening to the summaries from the previous discussions, day 1 and day 2. And I personally hope that actually there's already kind of, in the sense of what Piers just said, the first sort of ordering coming out really of the important points. And we will start with Laura. And yeah, Laura, go ahead, and I will keep time. You have 10 minutes.
Thank you. So my job is to summarize in 10 minutes the 70 minutes of talks and 25 pages of Etherpad that we had for challenges in climate modeling. So I'm going to kick off with Ruby, who talked to us about ultra high resolution climate modeling. So this is climate models with a resolution greater than 10 kilometers in the atmosphere and an eddy resolving ocean. So Ruby tells us that these models can be skillful without tuning, that they can be particularly useful for simulating extremes. They're much better at capturing storm structures and wind intensity and atmospheric rivers. In addition to this, they might help us to constrain cloud feedback, and they also might be useful for machine learning applications, particularly training of those. So Ruby was quick to highlight that ultra high resolution modeling is just one of the many tools that we need to use to address the problems that we're currently facing in climate modeling. So these are things that we're going to want to be using alongside modeling of subgrid scale processes, improving our representation of carbon and nutrient cycles, and ice dynamics, and also better understanding internal variability. So some of my favorite discussions that were going on in the Etherpad in the background were questions about what we need to do with vertical resolution to be consistent with the changes we're seeing in the horizontal, and questions about whether ultra high resolution models are actually better at simulating the large scale circulation, and whether projections from these models might be more likely. But one of my favorite comments was that ultra high resolution modeling is forcing a focus on process resolving scales. So it's causing us to focus more on getting things right for the right reasons, rather than just tuning our models globally. So on to our next talk now, from Tim Palmer, who was looking at the next generation of climate modeling. And Tim's big message was that we all need to think big. So Tim gave us example of the $10 billion investment in things like the Large Hadron Collider or the James Webb Space Telescope, and asked us what we would do with that kind of cash. He also asked us to think about what we could achieve by working together, particularly thinking about coordinated networks of exascale computers, and whether we could use these to produce coordinated kilometre scale global ensembles for decadal prediction. So Tim gave us some more arguments for moving towards kilometre scale modelling, including more accurate physics and less need for parameterization. But Tim also moved on to talking about better assimilation of observations that would come with these models, and thus better reanalyses and better initial conditions for our CMIP class models. From the Etherpad for Tim, we had questions about what we're already spending. That was answered actually in a later talk, that CMIP 6 costs us about $3 billion. And there was a lot of recognition that we can't simply compute our way out of the problems we have. So if we're not representing fundamental processes well, we're still in trouble. Our next speaker was Elena Shevlikova, who was talking to us about challenges in Earth system modeling. So Elena's top three challenges were the modeling of marine ecosystems and biogeochemistry, where we can now represent nutrient exchange, but coastal processes are still challenging. So things where we're looking at different resolutions and different systems coming together, still causing us trouble. Atmospheric chemistry was challenge number 2. So even if we have models where we have lots of atmospheric traces, we still need to be able to link these to oceans and biosphere. And the third example was land comprehensiveness. So we have few models that have interactive vegetation still, few models representing irrigation and urban management. So we're potentially still missing feedbacks in our models. And we still don't understand a lot of the major drivers of carbon uptake in the models as well. So from the Etherpad there, we're looking at how we optimize what we simulate, what doesn't require complexity, what does, and how do we test which processes and components we need for a given purpose. There are also, again, more calls for higher resolution. It's a bit of a theme. In this talk, particularly, we were thinking about carbon uptake and how high resolution might bring better ocean mixing, which might bring better carbon uptake in the oceans. And we also came back to observations here as well. So land sinks and models are under constraint. We see limited observations of land processes and some disconnect between modelers and observationalists here, which might be useful to resolve going forwards. Then we move on to Sabine, who talked about hydrological and regional modelling. So the focus here was on droughts and floods, which are 2 of the most devastating consequences of climate change. In addition to direct human impacts, we're looking at contamination of water and infrastructure issues there. So we still see that GCMs have better skill in simulating droughts compared to statistical models. And we see that skill there is still tied to representation temperature. So Sabine showed us some examples of modeling flash floods using the Ulysses model, and showed us that this model can still only capture these types of floods 1 to 2 days ahead. So there's a need for higher resolution inputs in those models and better observations for bias correction. And what Sabine showed is that when these models are able to capture floods, they still underestimate the magnitude of those events, So there's a need there for hourly precipitation, convection resolving models, and a fast coupling between GCMs and our hydrological models. So she asked the question of whether Destination Earth is going to deliver those things and progress in that field. From the Etherpad for Sabine, we're asking what hydrological models need to provide a complete climate service. So again, the theme of the day, we need high resolution simulations, but also for this field, we need a well set up and parameterized model. Our next talk came from Bela Fox-Kemper and Jeannie Lee on the challenges of climate modeling following AR6. So they took a number of challenges. We need to improve fitness for purpose of our models. So we're still seeing large biases in precipitation and large-scale circulation, which presents issues for regional projections. And we need to do a better job of quantifying uncertainties and the sources of those uncertainties. So in CMIP6, we still saw limited use of large ensembles, and we're still seeing a number of feedbacks and processes not considered in our models. The big challenge for CMIP6 was large near-term uncertainty. So CMIP6 did a much better job of sampling emission uncertainty in the future compared to CMIP5, but we're still seeing lots of uncertainty also coming from the representation of aerosols, model uncertainties, and our understanding of internal variability. There was questions for CMIP6 about how we improve our regional climate information in the face of biases. Do we need ensembles of regional models instead of global models? And do we need more studies that focus on process improvement for regional climate rather than just a large scale evaluation that's been the focus of CMIP6?
You have 2 minutes left.
Thank you. They also raised questions about how we select scenarios. So as I said, CMIP6 and AR6 were broader in their scenarios than AR5 and CMIP5, but we still saw big gaps between scenarios. And we also saw that there was no likelihood attached to scenarios, which meant that we find difficulties in probabilistic predictions, which a lot of policymakers would like us to provide. So AR6 really demonstrated the value of model hierarchies and emulators. We could see that our ESMs weren't spanning uncertainties alone, but they could be supported by our emulators. So from the Etherpad, we're asking what timescale should ESM experiments become available to input into a large assessment. So for CMIP6 and AR6, there was a very short time between release of the simulations and the production of the report, which caused problems with content. On now to the successes of CMIP6 and where we go next from Jean-Francois Lamarck and Matthew Myslinski. Big successes from CMIP6 were the structure. We had common data standards, metric packages. We had great extensibility. So we see examples coming out of that being COVID MIP. So CMIP6 was really an investment in structure that could then be leveraged for new science. We had co-located data and analysis for the first time. So things like the Cedar and Jasmine platforms and the platform at DKRZ. And as we go into the future from CMIP6, we're now seeing more projects using the aligned standards and structure that we had in CMIP6. And we hope that in the future we can increase access and continue to evolve the infrastructure standards. So CMIP6 was a $3 billion investment. Did we use it efficiently? We're trying to answer lots of questions, and we need to think about how we optimize resources. So questions about resolution versus ensemble size, and how to maximize the relevance of the simulations and the work that we're doing. So in the Etherpad, we're thinking about effective ways to deliver progress beyond CMIP6. So thinking about what was incremental, what was helpful, do we want to focus more on scenarios versus process understanding, and do we want to move to a better alignment with CMIP6? So the last talk of that session was from Pierre Fiedlenstein, thinking about greening of climate modelling. So we need strong mitigation of emissions globally. We all agree on that. And we want to think about a 50% reduction in emissions. But climate scientists fly more than all of the scientists, and scientists fly more than everybody else. So we're thinking about moving to virtual meetings and restricting travel to essential travel only, but prioritizing those who benefit most from travel to still be able to travel. We're also worrying about computers as a big source of our carbon footprint. While computers are becoming more efficient, we're increasing our consumption. So we want to monitor the carbon footprints there. So he put forward a target for CMIP 7 to halve its emissions relative to CMIP 6. And the Etherpad had loads of great ideas for how we might reduce our carbon footprint, particularly from travel, and lots of discussion of pros and cons of travel and different opinions on the value of Zoom meetings versus in-person meetings. And my favorite question there was, if CMIP was a country, what would its greenhouse gas emissions be and where would it rank? So I'm out of time and I will stop there. Thank you.
Thank you. Great summary. And without the slide, I really enjoyed that. Thank you very much. And I'm pretty sure there are many points to continue discussion, particularly also the last one, which in fact, just as one comment, WCRP actually decided to try to actually have 50% meetings virtual and only 50% in person, just to in fact cut down on emissions. And the emissions of climate models, we definitely have to keep an eye on. So thank you very much. We will have a discussion at the end of the session. So I would just move forward. The next summary comes from Chris Smith. Do you want to share your slides or screen or?
Yes. So I did put some slides together.
Yes.
So not as talented as Laura, who's able to speak off the cuff. So hopefully you should be able to see those now. So I was rapporteur for the Societal Needs for Climate Information session. And I sort of picked up two overarching themes that most or all of the presenters in this session covered. And the first one was the need for more and better communication between communities. Christy, who was, her talk was about the interaction of climate change and health, made the point that the climate researchers and health researchers often get things wrong when they don't work together. And then we had Rob, who gave the talk on the remaining carbon budget and how the media can take a concept, a physical science concept, and spin it in a way that is completely different from the original scientific basis that it was devised for. And then the third talk was from Yuri and Malte on whether one point here was whether mitigation strategies are resilient to climate change and for better communication between mitigation and adaptation communities. The fourth talk was from Chris Leonard, who mentioned, amongst many other things, the appropriate use of climate information to avoid maladaptation. So again, this is more linkages between the sort of Working Group 1 and Working Group 2 communities in IPCC parlance. And this was also touched upon by Mandira and Christie as well, better linkages between Working Group 1 and Working Group 2. And Mandira mentioned understanding and mapping the user landscape. So climate science that is tailored for users, particularly in Global South and developing countries. And a number of discussions in the Etherpad were related to this better collaboration between the three working groups of the IPCC and how we need to work together more closely. The second overarching theme that I picked up was development. So many of the presentations had strong development aspects. So Christy mentioned that sort of early warning systems for climate health impacts and extreme events, and for these upstream, downstream risks in mountain areas are one thing that the climate science can provide as a service. Impacts and issues are transboundary. So physical science doesn't respect borders and politics. A very interesting point I took away from Christie's talk was that the severity of health impacts is a function of development pathway as well as temperature rise. So adaptation and mitigation are important alongside the climate change that we see. We need greater involvement of marginalized groups in decision making, which was a point highlighted by Chris and Mandira. And the fact that many issues are multifaceted and many countries are dealing with multiple issues, and climate change is only one of them. And often poverty is a cross-cutting issue across many different areas of development. So moving on a little bit to a summary of the individual talks. So Christie mentioned that so the magnitude and burden of climate health outcomes is dependent on scenario as well as temperature. So these are the things that we are looking for in terms of the physical science here. So we're looking for estimates of the extent that climate change is causing illness, injuries, and deaths. We're looking for sort of estimates of magnitude and pattern of health risks under a range of climate and development scenarios. As I previously mentioned, we are interested in early warning responses for heat waves, to evaluate the effectiveness of policies and measures to increase resilience. We're seeking to evaluate the costs to individuals and health systems of the health risks of climate variability and change. And we are looking to estimate the health co-benefits of mitigation policies and technologies. And one of the final sentences that she had was really hit home as we should be mitigating for our health, and these aspects are really intimately related. So the second talk was so carbon budgets are a very, very simple concept, but they often get complicated and corrupted. So carbon budgets themselves have a long history. They were first mentioned in a Greenpeace report in 1997, but they started to take off as a concept around about the time of the fifth assessment report, between about 2013 and 2015. And they're extremely policy relevant as they influence climate policy, and they directly relate to net zero CO2 targets that many countries have now implemented. And then we have the Miller et al. Paper in 2017, which caused a media storm. This basically said that the carbon budgets, remaining carbon budgets predicted by AR5 models were too low, and a reevaluation found that we had a larger budget to limit warming to 1.5 degrees. And then sort of climate change skeptics jumped on the bandwagon to claim that climate science and climate models were wrong, and climate change was all a sham. And Rob was using this as an example to show how the media narrative shift from a scientific concept to an opportunity to attack climate policy. Our media landscape has fortunately improved. The IPCC special report in 2018 had a lot to do with this. But there are still nefarious actors looking to jump onto manufactured controversies. And this is something that we need to look out for as a community.
You have 2 minutes left.
Thank you. Okay, so the third talk was mitigation by Uri and Malti. And this centered around three key questions. So firstly, how much warming do we expect for a given emissions pathway? Second, are mitigation strategies resilient to climate change? And thirdly, how can we better integrate Earth system science and mitigation studies? And this is really focused around those Working Group 1, Working Group 3 interactions and how we can provide better climate science for mitigation. So Uri and Malti had some requests from the physical science community. So we were interested in warming from feedbacks on uncertainties, zero emissions commitments to different forces, and Earth system responses to negative emissions. So we're looking for leaner and more flexible Earth system model tools, including continued development of emulators that are more with UN climate policy goals and deep mitigation around 1.5 and 2 degrees of warming, and not wasting resource on high warming scenarios. Okay, so the fourth talk was by Chris Leonard on impact and adaptation.
You are breaking up in between, but just go ahead and continue.
Thank you. So half the world's population live in hotspots vulnerable to climate change. There are issues around compound risks and simultaneous extreme events. And we're looking for climate science to strengthen resilience and reduce vulnerability. And there's a list here of how to contribute to
Maybe you can switch off your camera.
Examples
this might help.
Sure, yes. Yeah. Okay. So Chris also made the point that improving the geophysical aspects of model uncertainty and timescales relative to adaptation, such as subseasonal to seasonal timescales, and the lining up of the CMIP process with Working Group 2 and zooming in on impacts. And finally, the final talk was from Mandira on communities in the global south. And this was focused on the third pole, the Hindu Kush Himalaya region. And Mandira pointed out that mountain regions are warming faster than the global mean. And there are several challenges in these regions. So remoteness, network density, data sharing, adaptive capacity. But there are also several opportunities. So we can sort of assist as climate scientists by providing tools and technology for capacity building, frameworks for reducing risks, including hazards, exposure, and vulnerability, gender mainstreaming, institutional capacity building and use of projections, identifying gaps and needs, and as I mentioned earlier, stakeholder consultations. So developing links with these communities and determining what is actually sort of important for these communities. So in the interest of time, I will stop there. Thank you very much.
Thank you. Great summary, and really also highlighting, in some sense, kind of why do we do the modeling? Where is this information needed? And I think that for also what Piers was addressing earlier, I mean, how do we digest this now, and how do we move how do we move this forward? I think this session and your summary was really very, very well received for this specific purpose as well. We continue now and go into day 2, and Eiko Voigt will provide the next. This was probably not pronounced properly. I apologize. The next summary.
It's German, so it's Vogt. You should know. Vogt. So yeah. So I will share my screen. Wait a second. So this was the first session of day 2, shared by Angie Pendergrass and Roland Zeffereyan. Yeah, so there were 10 talks actually, so I'm going to be quick on these. I just listed them here, and I thought I would just give my one-sentence summary of all of these 10 talks at the beginning. So we started with high-resolution modeling from Daniel Glocke, and I would say, well, there was this argument which I liked about he calls it strong resolving models being simpler models because they use closer to the physics. And one application that I kind of would highlight here is the idea of, can we use these models to avoid climate surprises? So is there something structurally different in these, what we believe are models better suited in physics than in GCMs we're using today? The next talk was by Stefanie Fiedler about composition climate models. And so there's a lot of research on how aerosols impact, for example, circulation of the atmosphere and the ocean, and SST patterns in particular. But there's also this idea that these models can become fairly expensive. And so how much can we afford when we couple chemistry to the fluid dynamics? How much ensemble size, how much resolution can we do? And how much do we need to do? That's also a question, I think, that's open. Then we had a talk by Zeb Nichols about model emulation, simple, or you could call emulators or reduced complexity models. And here what I liked was this idea that, well, you have to realize that these models really rely heavily on what we have done in CMIP. That's something that we should appreciate as a community, that we should not take for granted. That's the value of CMIP. And that these models are very well established on the global scale, especially for temperature. But it's a bit open how we can kind of extend these models to the regional scale. So regional temperature changes, regional precipitation changes, maybe even precipitation extremes. The next talk was by Claudia Tebaldi about societal decision-making and model integration. So here the question is, well, if we want to be societally relevant, we have to take our climate information and make it accessible for society and decision makers. So what does it mean? And so there's this question of integrated assessment models and ESM models and how we integrate them. She proposed, or she discussed, two possibilities. One was to hardwire integrated assessment models into ESMs, which might or might not work for the reasons that she discussed, or a more indirect approach, as I would interpret this, and to say that how can we digest Earth system model information into integrated assessment models, and here emulators would seem to play a role again. Then talk number 5 was by Katja Friele about climate change and socioeconomic impacts. And I think at least what I got from this talk was to say, well, instead of attempting to make a direct link between weather and impacts, this idea of making this a link via what she calls biophysical predictors. For example, people affected of water scarcity. And these predictors could be obtained by models which actually exist, namely biophysical integrated assessment models, which are already, as I understood, run by EasyMap. Then we had a talk by Tomoki Miyakawa on what we need to do to improve our models. And so what he highlighted is the fact that we, again, also going back to Daniel Klocke's talk, that we are now able to, we are beginning to be able to run 5-kilometer climate models. And the two challenges that we will face in the coming decade or so is this idea of how do we couple atmosphere and ocean in these models, and what does ocean biases mean. And in the atmosphere, and I do believe that the kind of convection problem, at least the deep convection problem, is solved. But that just means that we have to solve the microphysical problem. But it might be a much better way to work on microphysics in these sub 5-kilometer models than in current GCMs. And he also made the point that I found interesting, that because of computational aspects, it might be much easier to do ensembles of decade-long simulations in these sub 5-kilometer models than doing a long 100-year simulation. So that's an interesting aspect to consider. Then we had Paul Durack talking about model evaluation. So he highlighted the point of that how we built a community around this idea of using standardized data and standardized analysis tools, which I think is a strong point in climate. And he highlighted for the future the need to go from the global scale now onto the regional scales and process scales to develop these analysis tools to look at this fitness for purpose evaluation for regional climates and processes. And also he highlighted again, also relating back to day 1, this idea that we need to go beyond what is called silos, so beyond disciplinary research we often tending to do. Then we had Nicola Maher on large ensembles, and she was highlighting a few of the remarkable successes that large ensembles have enabled over the last 5 or 10 years. For example, this idea of how do we actually, as a community, maybe proactively do expectation management when it comes to what we should expect as the success of mitigation on 10-year timescales, which was interesting. Like, even if we are successfully mitigating, see stronger warming. than we would want to. And then this idea of partitioning sources of uncertainty, which is very helpful. And she highlighted many applications that she could imagine, for example, the signal to noise problem, but also applying large ensembles to extremes. But she also mentioned a few others. Then we had Nick Golich on processes that are currently missing. And he decided to focus on one particular, I guess for good reason. So he said, well, carbon models typically miss interactive ice sheets. In particular, what they're missing in the Arctic is the coupling of the ice with the ocean, which can lead to important feedbacks for the stability of the Antarctic ice sheet. And then I also took the liberty to include Libby Barnes' talk on explainable AI in climate science. And the things that she mentioned or highlighted here is, well, it's really a remarkable extension. Explainable or interpretable AI is a remarkable extension of the toolbox we are having in climate science to do things better and faster, which of course we always want to, but also to do or learn something new. And that's, I think, an interesting aspect of AI as a tool for learning, understanding, not just for learning for models. Good. And then we had, as the others also highlighted, we had this 11 pages of Etherpad, which I managed to read once or twice, but so I'm not going to give you an exhaustive list of this, but I give you a selective list. So the few things that kind of struck me. One was, and maybe it's only semantics, but maybe it's important to think about this. How do we call kilometer scale models? Do we call them storm resolving models? Roland just brought to my attention that SRM is also solar radiation management. I'm used to SRM as storm resolving models, but is storm resolving model even a good name because storms in the exotropics are much bigger? And do we need to think about this? The other aspect is, of course, storm resolving models are not going to change all our problems. I think we kind of know that, but sometimes people seem to believe that we pretend this would be the case. So also mentioning of the interactive methane and climate chemistry models, which would be needed, but also in the question of, well, how much coupling do we actually need to solve the chemistry part of the climate puzzle? How much coupling can we avoid? So also mentioning of an ongoing, when it comes to integrated assessment model, ESM integration, ongoing project in the EU, funded by the EU, the ESM 2025 project. And I also like this idea of using emulators to free GCMs from the burden of scenario runs in CMIP. So CMIP is kind of dominated, or has been dominated for a long time by CMIP scenario runs. But now that can be done by emulators. So, and this to me means we could use CMIP GCMs again as tools for understanding instead of tools for making predictions. That's an interesting idea, I think. So also this question of how do we actually balance kilometer scale modeling, which is very heavy on computation, versus large ensembles, and can we do both, or do we need to do both, or what would we prioritize? And that's of course not clear. And this question of what is the information content of kilometer scale models? What does it actually mean? How do we look at this? What are the metrics we are using? Do we just always cross-grain again to 100 kilometers and do our typical workflows, or how can we do better?
2 minutes left.
Yeah, perfect, because I only have 2 more slides. This is now completely, oh no, there's one more, I forgot, sorry. Also, as mentioned, that came up in the discussion, an interesting idea. And so Daniel proposed this Turing test, and he said, well, all these models look reasonable and we cannot distinguish by eye, but then it was brought up that, well, the Turing test is insufficient. What we really need is a Kar's law test to verify our predictions or make them reliable or test whether they are reliable. And so I think Ken, or someone, I think Ken, it must have been Ken, phrased it as saying, if we had 20 models that passed the Turing test, would they have higher accuracy in making the same predictions, or would they just scatter like our current ensemble? And what would it mean? And I have 1 minute maybe. So, and this is completely subjective. This is only my own thinking, but I thought I could step out of my rapporteur role and just give my 2 cents. So this is maybe what I got the impression from climate modeling as we have it today, and CMAP models are in the center of climate modeling, and they are kind of giving input to all of these other models, or they're being coupled to all these other models and approaches. And if you think, if I was asked to think big, then maybe what we should do, what we could do as a community is to think, well, maybe this is what it should look like in 10 years. GCMs kind of move out of the centerpiece of what we are doing and really put the kilometer scale in the center. At least we could try to do that, and that's something that I would like to do. But of course, that's my own opinion, so I will leave it like this. Thanks.
All right, thank you very much. Again, a great summary of the discussion. And in fact, it's really nice to see all this digested information already, including the information from the Etherpad, which, for instance, I didn't have all the time to read it in between. We come now to the second day 2 contribution from Matthew.
Good evening, everyone. Right, so I got a fairly easy session in the sense that there's only 4 talks, so I'll run through those relatively quickly. My slides will let me go forward. There we are. Okay, so first up we had Hisashi talking about computing hardware development in Japan. So the development of the Fugaku HPC in Japan sort of co-designed that they were involved in co-designing the hardware suitable for weather and climate science models with the manufacturers. So trying to take an approach where they focus more on CPU-based processing to make the parallelization easier, and sidestepping the GPU hybrid approach that's been taken in many centers. One thing that was sort of also mentioned is that sort of very keen to take computers that are to produce computers that are more advantageous for the client weather simulations. So trying to get involved from the early stage with the designing of the chips. A lot of performance improvements are available via activities like reduced precision or careful use of memory. It's been mentioned earlier by Tim Palmer as well, and also by careful consideration of storage at various levels within the infrastructure. In the Etherpad, there are other technologies were also mentioned that are in the pipeline. Tensor processing units, a new one for me that could have a role alongside CPUs, GPUs, even FPGAs, field programmable gate arrays, and possibly in the near to more distant future, memory processing units which could provide a valuable performance increases. Co-designing the architecture would could potentially provide an order of magnitude performance increase, but this would need broad engagement of the climate science HPC community with the chip manufacturers to make this viable. That was followed by Francois talking about model development in South Africa and the Southern Hemisphere. So that the Global Change Institute and the University of Witwatersrand in Johannesburg are putting together a new Earth system models with support from CSIRO in Australia. They've put together a cube sphere model and taken that, applied that to global climate change and paleoclimate case studies. And again, introducing downscaling through a stretched global grid to enable the define a resolution around the area they're interested in. Having an ASM developed within Africa is potentially key to ensuring that local facilities capabilities can be developed in climate science and provide a clear career pathway for African climate scientists and regional services. And one thing from the Etherpad I picked up, how can we link sort of new institutes like this and initiatives to the global community regarding data sharing and information. Okay, Mario talked about the results from CPMIP and looking towards minimizing the carbon footprint of climate modeling. So we presented some results from BSc looking at the whole range of ways that carbon is emitted from computing infrastructure, buildings and travels. Their results from 2018 show around about half of their total budget comes from computing infrastructure, followed by a third from travel. This, metrics from CPMIP were presented, sort of those that came from IS-INES as 11 institutions and 32 models there. And analysis of the BSC facilities also shown that the costs of running data and transfer and storage facilities can be significant. From the ETHPad picked up, it'd be good to factor some of this thinking about the carbon emissions in when considering future activities, and to embed monitoring of it and recording of it within our workflows. We'd also be valuable if we can consider the impact of our current infrastructure, such as the distributed ESGF system, as part of the analysis. Use of cloud may be more expensive in isolation, given some of the numbers that can be bandied around. But if multiple copies of data can be replaced by one, it could well be more efficient. We would, however, need to construct a collective, perhaps international funding mechanism to make this happen, which could be challenging to organize, but nevertheless worthwhile. Okay. Follow up, we've got sort of Tapio was talking about novel climate modeling approaches and AI-aided hybrid modeling. So the requirements we have for our models are quite challenging, and we need to be able to rapidly iterate them, run models to test things out. We still need to increase accuracy and quantify and have quantified uncertainties. To get there, Tapio was proposing we need to include tools to learn from the data, such as AI and machine learning. Resolution alone may not necessarily deliver. Deep learning techniques coming from the machine learning background are very data hungry and difficult to generalize or interpret and pull out the physical understanding behind them. The reductionist approach that we have struggles with complex systems as you start building up more and more complex sets of equations in an attempt to understand what's going on. Closure functions are good targets for machine learning approaches, particularly where process level observational data isn't available. Entrainment's mentioned in this case. And we need to learn from diverse data that we've got by augmenting the process-based models with these AI approaches, bringing everything together, learning from the climate statistics we have and building on existing publicly available tools. That's a very broad brush across those 4 talks. And my apologies to the speakers if I missed any critical points, but that's me done.
Thank you. Great summary, and I really like this because it also raised a couple of extra points that we might want to pick up again in the discussion. And just as a remark, in fact, Pierre Friedrichstein had a talk on the first day on the carbon footprint. He did send a few of us a manuscript that apparently just came out about the carbon footprint of astronomy, which we probably haven't thought about, but apparently it seems to be enormous. And I think at some point, climate scientists also need to face that problem, and we have to think about it, like where to put our computer centers and geothermal energy or whatnot. But this might be something we have to come back to at some point. I have now on the list here kind of brief recaps from the 3 breakout groups from yesterday. And I assume the rapporteurs are prepared to give brief key points from your discussion yesterday. Anybody? Amanda, do you want to start very briefly for Breakout Group One?
Yes, I can, yeah. And I have a slide just to show quickly, hopefully.
And meanwhile, the other can prepare themselves mentally, at least.
Do you see that okay?
Yep, perfect.
So this is just a very brief summary. Obviously, last night we went through a more detailed review of what was discussed, but here's just a few key points that hopefully will feed into the discussion. So the first one was around, CMIP specifically and sort of how CMIP is organized and structured. It was perceived that, CMIP 6 had many advances on CMIP 5 in terms of having specific MIPs to address science questions, which was good, but could we move beyond the ensemble of opportunity approach? So specifically thinking about how different modelling centres contribute across the different areas that have been talked about at length in the meeting so far. So the large ensembles, the high resolution modelling, the process understanding. And that seems to be something WCRP, could clearly take a lead on or making recommendations around. This has already come up in the summaries already, and particularly from Chris about the need to sort of have closer synergies between Working Groups 1 and Working Group 2, and having these co-design approaches to ensure that, you know, the work that is being delivered from the sort of Working Group 1 community is meeting societal needs, that timelines for the Working Group 1 and 2 reports are kind of better aligned, and that we de-silo from the sort of Working Group 1 approach and think more interactively across working groups. There's been a lot of discussion about, you know, sort of complexity, resolution, etc. of models. I think the key point to bear in mind for us is really about the roles of model hierarchies, with using Piers Forster's phrase, horses for courses. So in some cases, more coupling may be needed to tackle certain problems, but clearly that may not be needed for all problems. So we need to kind of have a flexible approach to modeling that accounts for the variety of needs. We talked about regional climate change as a focus. Clearly, that's something that WCRP has, you know, historically had a focus on, but there's still key knowledge gaps there, particularly around the roles of atmosphere and ocean circulation. And that's something that, you know, is pointed out, the Lighthouse activities are going to be picking up as an emphasis. And finally, just around deep uncertainty, and moving beyond the idea of needing to kind of try and come up with the best probabilistic estimates as possible of certain events, accepting deep uncertainty and working within that framework around, for example, the occurrence of tipping points, thinking more about, you know, storylines as tools to look at those low likelihood but high impact outcomes as another approach. So I'll finish there. Thank you.
Thank you very much. Great summary. So we will now continue with the second breakout group. Anybody who wants to summarize this?
Detlef, I don't see Zeb online. Zeb Nichols.
Anybody out of the group who would like to briefly bring forward a few points, key points? No, then maybe we skip this and go to the breakout group 3.
Detlef?
Yes.
Roland's talking. The Zebs put some summary in the Etherpad, so maybe you can read them or I can read them. So if you want.
This is the Etherpad from yesterday, right?
Yes.
Okay, maybe if you have it open, I have the Etherpad open from today. Maybe you can just read it.
Okay. So I read the 4 points of Zeb summary notes from the breakout of yesterday. So point 1, it seems clear that there is no model that will do everything. So interoperability is key. We need to be somehow flexible and modular with the modeling activity, and simply think as of things that need to be compromised or trade-off between complexity resolution is somehow too simple. So no best point in resolution and sample size, complexity, space, but flexibility and interoperability is important. So point 2 is a key question of interest is key. So we need to think about why we are doing things and what we are trying to achieve. And Tim Spalmer's provocative point is, what's the point of complexity if the coupling between hydrological and carbon cycle model in Earth system model is not properly resolved, and if your hydrological cycle is wrong? So we didn't get more time to think about this. Point 3 of Zeb's note is there isn't a scale break that is achieved as we increase resolution. Rather, we move on a continuous spectrum, and there was a discussion on the benefit of increasing resolution versus increasing the use of AI type approach. And the last point is a more general question of CMIP. Should CMIP become more policy focused? It's a question. And we need to reshape multimodal approach So either in response of refining the question of interest for CMIP, or because of other change in the focus or the scope of CMIP. And should we as a community have a more spearhead work / institution like the CERN for climate and the CERN for atomic physics? So that's all.
Okay, thank you very much. These are certainly important points, and as we said in the beginning, of course, we talk about CMIP, but CMIP is not the main focus of this discussion. But of course, it is. We cannot. Well, I shouldn't say ignore it, but we cannot neglect it either. And of course, one of the questions we are discussing here is where should actually WCRP put its focus of modeling in the future. And in that sense, is also kind of the future use of CMIP within WCRP that we need to think about and discuss and identify really the important points that WCRP should pursue in this respect, not just the operational part, but it's certainly a very important aspect that needs to be clarified. So thank you very much. I think that we will have a discussion, a 20 minutes discussion, and we will certainly come back to one or the other points that you just summarized. Let me just see if Masa, or do you want to briefly summarize our breakout group, or Junyi probably? Junyi, yeah.
Or Junyi, or I can do that.
Junyi, do you want to go ahead, or?
Okay, so yeah, let me share the summary file and give you some summary for that. So can you see the slides?
Yep.
Okay, so there are several important points we discussed. The first point is to further improve observation, reanalysis, and paleoclimate information. In particular, we heard about these kilometer scale simulations, opportunities and challenges, limitation a lot, but to further validate and evaluate those kilometer scale simulation, we really need an ultra high resolution observation system. In particular, we still have lacking the reliable land surface observation, including soil moisture and vegetation. And also we need more data for vertical structure in the atmosphere and in the ocean. So there are many activities going on, but we may think about more coordinated field experiment across centers, particularly for the vertical structure of cloud, ocean, and etc. And also we discussed about the better utilization and improvement of paleoclimate information to constrain climate models and to better understand the climate changes. The second point is the better coordination and better communication across many communities and modeling centers. Then WCRP already have played an important role for that kind of coordination, but we still need better coordination, especially to fill the gap between global climate assessment metrics and regional information for impact studies, also between model development communities and the climate scientists using those models for evaluation and for process understanding. And also need to fill the gap between conventional climate modeling community and storm reserving modeling community, and also need to better communicate between climate modelers and also NWP groups. We already have several activities between WCRP and WWIP, for example, S2S project, but we may need to consider more coordination between two groups. And we already discussed a lot regarding how we learn from NWP activity and also seamless modeling activity across operational centers. Then we still need a hierarchy of models to better understand all the processes. And that part we still need to push it forward. Then the next issue is the further development of common evaluation tools and metrics. And we already have several very good examples like CLIVA, climate model metrics, and also ESM by tool. But still, for many climate researchers, especially in the developing countries, we are not that easy to utilize all those evaluation tools yet. So probably we may need to further develop those common metrics for better use, easier use. Easier use. Then, although we have a good metrics for global measurement or global characteristics, but we are still lacking to have a better metrics to capturing special patterns or regional details. So this part, I think, also important to consider in near future. Then also we discuss about how to better address issues on higher climate sensitivity in some CIMI-6 models. And actually those higher climate sensitivity models have a better simulation for recent warming, particularly over the land region. But certainly they also show much higher warming in the future. Then actually we have that high confidence regarding the reliability for such a high temperature warming in future. So this part we still need to think about further. Then also there was discussed whether we have a right metrics for modeling tuning or whether we have a sufficient condition for constraining climate sensitivity. Then also we have other issues. Then maybe you can refer later on. But Masa, do you want to add something here?
No, I think that's a good summary. And we talked also, maybe I just would like to add one thing about, we talked about modeling what is measured. And that's valid for many things. A good example is cloud, but it could be done for other things and coordinated. And also the estimating the parametric uncertainty. I think you listed it somewhere. But, from observations.
Yeah, and I think the first point that you made is probably related, for instance, that satellites measure radiation and the models should actually project their fields onto these quantities, what the antenna would see, or what did you mean?
Yes, that's exactly the case.
Yeah.
And so it's also the case for land surface and so on, other measurements, other types of measurements.
Yeah, and this is already done in the weather forecasting simulation approaches and so forth. But yeah, I think this is very good, a very good summary. And thank you very much. We now have, if I see this, probably something like 15 minutes or 20 minutes left for discussion. And I just suggest that everybody who would like to make a contribution or ask a question, just raise your hand that I can see this, and then we can go down the list. And I do see already Tim having the hand raised. Tim, go ahead.
Hi, thanks, Detlef. I just wanted to make a couple of points, hopefully as quickly as possible. In the very last summary, I just wanted to kind of emphasize the bullet on seamless prediction. And I want to relate it to one of the earlier comments about what was called the Carr's law test, a kind of, going beyond the Turing test, which, by the way, that alone is a tough enough one to pass. But the Carr's law test was something to do with reliability of forecasts. Now, the problem with climate change is that A, it only happens once, and B, it happens in the future. So we have no idea whether our predictions are going to be reliable or not. So the only way to test whether our ensembles are reliable in a probabilistic sense is to test them on past occasions. And that's precisely what, is done in NWP and seasonal prediction and to some extent decadal prediction. So if we want our models to, if we want to even evaluate whether the models pass the Carr's law test, we have to test them in seamless mode. We have to test them in NWP, seasonal and decadal. And I think people who, have a great affinity to CMIP might be in for a rude surprise if they were to test the CMIP multi-model ensemble in sort of medium range prediction mode. I suspect they'd find that the probabilities are far from reliable, but that's my own gut feeling. But it's based on the experience of ECMWF over the years with moving to high resolution. I mean, that's one quite clear evidence that going to high resolution has made forecasts much more reliable than they were, 25, 30 years ago. The second point I'd just like to very briefly make is to bring up the Miller et al. Issue that was raised yesterday in the media, how it caused a great storm of controversy. And my own view is that this, to some extent, reflects badly on us. And I think, whilst we in these kind of groups are very open about the, the deficiencies of models, this doesn't actually get reflected in public outreach. And I think one of the worst offenders are the Summary for Policymakers documents in IPCC, which expunge pretty much all deficiencies that our model systems have. And as a result of that, policymakers and politicians have a kind of belief that climate modeling is a done deal. We've got as far as we need to go, and really the effort now is on trying to find ways to mitigate carbon emissions. There's currently not much enthusiasm, I would say, in political circles to fund large climate modeling projects, because most policymakers believe models are pretty much fit for purpose as they are. And that's, as a result, I think that's partly our own fault for, not having the guts to say that, there are still issues and we're not confident about everything. And I think the Miller et al. Is an example of how that blew up in our face. And I think it raises kind of profound issues about how we communicate uncertainty, not just amongst ourselves, but to the public and to policymakers. Thank you. That's all I want to say.
Thanks, Tim. These are really good points. And in fact, the coming back to the latter one, I often, in fact, have the feeling, and when we talk to the press, we usually say we cannot say because we still have to do this or that. And so often I do actually have the feeling that we might, in fact, criticize our own models so much that they might ask us, so what do you believe? And I think what you say is that we have to have the right balance between pointing out that what the models can and what they still have to do better. And I completely agree on that point. So let's actually continue now. Masa, you have the hand up, and then Andres afterwards.
Yes, so I just wanted to make a comment following Tim's comment on the seamless approach. This is really something we talked a lot about in BOG 3, and we stressed the interest of coordinating experiments for the hierarchy of models, or for the suite of models addressed by seamless models. So that's a topic for future discussion, I guess. And about model biases, I think we shouldn't forget that we are talking about climate change and not only about present climate. And one way to Tim was saying we should go to the past, but I would advocate going even further in the past. As you all know, I'm a paleoclimate modeler, and there's a lot of issues that are outstanding for a long time, and
it's still past. Paleo is also past.
Yes, and one avenue for improvement, I think, that we should make public is really about the hydrology, so that's also something that we discussed yesterday. Thank you.
Yeah, thank you. Very good points. Andreas.
Yeah, thanks. This is just a quick comment that was triggered by what Daniela actually wrote in the Etherpad today. She mentioned the Codex flagship part study over the European Alps, where they ran these kilometer scale models on regional scales. And I think we could do much better in coordinating or connecting regional efforts with global efforts. Like, we have a decade of experience in running kilometer scale models over regions. And I think we can learn something from this, but also, like, the regional modelers can learn a lot from the global modelers. And there's very little interaction between those two communities. So this is something I think that we should really tackle.
Yes, very good point. In fact, we heard that now and several places that the communication or the interaction between different communities is very important. And that probably is also true that the storm resolving or kilometer scale modeling people might become a community now. I think it's very important to keep them connected to the larger scale modeling communities that we don't really separate. I mean, we really need to work together on these. So further questions? While you're thinking, what came actually into my mind while I was listening is that, and this might in fact go also to Tim and others. We heard yesterday where we need to go in this direction or that direction, and we are not ready. And sort of also in the background, we started to wonder how much do we need to wait and have one part ready before we start spinning up the other part. And so, for instance, the dynamical part, we all know we really have to have higher resolution, but I don't see that we should actually wait with further developing the chemistry part or the hydrology part and others. And I was wondering if there's any comment on in particular this interaction of different communities and go beyond the typical WCRP community. I'm not sure if Tim, if you have any comments on really what comes first and what comes next.
Well, I think my own view is that we have such a kind of a diverse community that we can do lots of these things in parallel. I mean, you mentioned hydrology. We have some pretty sophisticated hydrological models these days. And, clearly I would think the main uncertainty in predicting, flooding and so on from rivers is coming from the precipitation input. So, I mean, I think the challenge with chemistry is keeping it relatively simple. And that's where I think AI and some of the things Tapio talked about will probably play quite a big role there.
Okay.
So I'm keen that we can do things in parallel.
Yeah. Okay, that's good, and I think the precipitation is a good point. Doug, do you want to continue? Doug, and then Daniela.
Yeah, I was just going to build on what Tim was saying about testing our models in past cases, and when we do that in seasonal and decadal predictions, we do find actually that they are seriously deficient in predicting atmospheric circulation changes. I mean, we find that they're doing something right, so there's skill there, but actually the magnitude of the changes that the models actually simulate and predict is much smaller than what actually happens. So this, I think, is a serious issue. It's not really been highlighted, I think, in any of the talks so far. And if this kind of continues, this underestimation of atmospheric circulation, it also applies to projections, then we could be in for some quite surprises, I think, in the coming decades.
Would you call this model improvement to come down to the? Or do you think resolution will solve this problem, or is there something else that needs to be worked on?
Well, so the evidence is that resolution may improve it, but we may need very high resolution, so that maybe the kilometer scale resolution that people are talking about. But if we can't afford that, then maybe it might be possible to build some parameterizations. We don't really understand why the error is there at the moment, but if we can understand it, we might be able to fix it.
Okay.
Doug, could I just chip in to say it's not just that surprises will happen. I mean, they have happened. I mean, the heat wave in British Columbia was just 1 million miles outside the CMIP, range. And I'm pretty sure the flooding in Germany and China and so on, they're just way outside what CMIP can do. So I think we're already seeing the phenomenon that you're talking about.
Yeah, agree.
Okay, thank you, Daniela. Or Angie, do you want to speak right to this problem, or?
Well, I just wanted to mention about the
the Pacific Northwest heat wave. It's not actually way outside of the realm of what CMIP models we're getting. I presented a poster at AGU where we used some simulations from this ensemble boosting technique from Reito Knuti's group at ETH, and other folks also had similar results, that if you were to take the model seriously, you would have seen events like this.
Well, I mean, the data I've been shown contradicts that, so I don't know where we are, because I can almost probably find on my computer a slide which shows British Columbia way outside the CMIP range. So I don't know what to say.
Okay, I leave this up to you to clarify on the in the background. And we continue with Daniela and then Pascal, and we have the 4 hands up, and I think then we have to wrap up.
Yeah, so I think, Tim, this clearly shows that the communities need to talk better to each other, and because also in the regional climate modeling community, the precipitation amount for the German flooding was not way outside of what models have projected. So probably the location was a bit shifted, but it really depends on what we are looking at. And I think I have 3 or 4 points here. So one is, I really appreciate the discussion about further improvement of the modeling and understanding. And I think here, when we come to the more high resolution scale, it's really important to connect better to the data observation experts and those who are working with sensitivity studies, developing out of data and data analysis, new parameterizations on their specific high resolution scales. So I think that that's one thing which I would like to see a bit stronger. Again, it was strong maybe 20, 30 years ago. The second point I have is I'm not so sure that we really have some metrics to identify which model is fit for which purpose. And if we would now look a little bit at the outside world, not only at our interest and curiosity and better understanding, but selling WCRP knowledge better to the non-WCRP community, I think we would all benefit from having a more clear wording in which modeling efforts, which experiments, which setups can be used for which purpose, why and why not. Where are the major uncertainties, but where are the major certainties? And with this, I would even go one step further and say, and we discussed a little bit CMIP, but I wonder if we do have a kind of a fast task force or group which would be able to react with modeling and analysis studies on policy requests about what is the influence of a specific solar radiation management option or an adaptation option or whatever mitigation option, so that we could give answers to policy ideas of mitigation or adaptation. We now have this huge technology push in the back on SRM, which will inform us in the next couple of years with this topic. And I wonder if we have could develop a quick task force or a quick group, because the big modeling experiments which we are doing, they are too slow to answer those. And we haven't really discussed this yet in depth, but I wanted to bring it up here today. Thanks.
Thank you, Daniela. Let's actually move on. I think this is an important point to address, but also what sits in WCRP and what sits in a climate service part. I have now Pascal and then Benjamin and then Baylor, and then we actually come to the break.
Yeah, so I also would like to be a little bit provocative somehow, because of course we need to improve the model, the processes, resolution, and so on. But I'm not sure we can do only in parallel, because when we think where we are today compared to what we thought we would be 20 years ago, we are not that far in the construction of this Earth system model. And part of it, I suppose, is because we are developing things in silos, where each community is developing its component, the own components, and then we couple them, and then we're losing time because we are not thinking altogether what's the level of complexity, the consistency between those models, and why we develop this coupled system. And also what we don't know really well is when we have everything coupled, we don't know how to analyze that. How we analyze those feedbacks on the tuning, the states of the model, variability, and so on. So I would like to come back to some heavy criticism of Wcrp from the review, who propose very different things to it. Something like think coupled, all coupled, and develop the things that are needed for the fit for purpose for the questions. So we should really think about it. Otherwise, we will lose time and have very high resolution components, and we will never be able to understand the full coupled system we want to have.
Thank you, Pascal. Benjamin?
Yeah, thanks. One more comment on the ability of the multi-model to prepare us for extreme events. I guess, can I share my screen? Is that possible? Just one.
Yeah, you
one
need
slide.
to push the screen, share screen button. Yeah.
You see that?
Yes.
Yeah. So this is a time series, bias corrected time series of maximum temperatures in the weather, the position corresponding to the weather station which recorded the most extreme outlier in the Pacific Northwest last year. And you see a moving extreme value distribution at the 10-year, 100-year, and 1,000-year level. The point is that the event it looks like it's about a 1 in 10,000 year event, and if you take a moving extreme value distribution. But the main point to take here is that the entire CMIT5 distribution is represented here, which represents about 15,000 years worth of individual simulations. And so to capture the probability of a 1 in 10,000 year event, broadly, we need to be working with 10,000 years worth of data, which an ensemble like CMIT provides us. So when we can't fool ourselves as a community into thinking that building a model which is capable of resolving a higher resolution at 1 or 2 orders of magnitude or 3 orders of magnitude higher computational expense is necessarily going to better prepare us for events which are fundamentally highly rare. Because they're rare, we need to be able to run models for a long period of time, and we need to sample the parametric and initial condition ensemble, initial condition uncertainty extensively. So I'm not arguing against the value of high resolution events, but high resolution models, but for the specific purpose of preparing us for extreme events, we need capacity to have large numbers of years. We can't expect that we'll be in a position in a small number of years that we can radically reduce our uncertainties in the projection of this kind of event. That's all.
But sorry, I mean that statement about 1 in 1,000 years assumes a stationary climate, and nobody.
No, it doesn't. No. My plot showed a moving distribution.
But nobody believes that's a 1 in 1,000 year event, do they? I mean, I've never heard any climate scientists say that's a 1 in 1,000.
I said 1 in. I said 1 in 10,000 year event.
10,000 years. Sorry, 1 in 10,000 years. Even worse. In at this particular point in time, by the end of the century, it will be a 1 in 1,000 or 1 in 100 years. But do we think it's 1 in 10,000 years now? That's the point. I mean, we believe that climate change is having an impact on that temperature, which makes it go way above or way whichever direction you're talking about, less than 1 in 10,000 years. So in
the context of CMIT5, that's accounting for the historical, allowing for a bias correct ensemble. It comes out at about a 1 in 10,000 year event. That's assuming that you can bias correct the historical CMIP5.
Right, and it might well be a 1 in 10,000 year, or it might be that it's a much more likely event that the CMIP models are not capturing, and that's the whole problem.
Exactly.
And I think when you look at the dynamics, that's extremely likely, because it was linked, for example, with an atmospheric river of moisture, which the CMIP models don't capture in any.
They don't even resolve it, right?
They don't even resolve it. So
Yeah,
I think it's more likely.
My point is not whether the CMIP5 models are right. My point is that even if you had a model which was theoretically capable of resolving the atmospheric rivers or whatever, which were necessary to produce such an event, you wouldn't be able to do enough years to assess the probability of that event occurring in a given location.
I think that point is well taken, and in the sake of time, we have to take one last comment or contribution from Baylor, and then we have to break for 5 minutes to get into the next breakout groups. Baylor.
Sure, I'll try and be quick. That left. Sometimes these kind of conversations really confuse me, because we have a lot of very good ideas all going in different directions, and then but there seems to be sort of a sociological effect that we'd all like to be doing the same kind of simulations, and CMIP has proven that there's an enormous strength in being able to compare models versus models. So multi-model is critical. Is it scores of models? Is it a handful of models with scores of different science questions we're going after? And then the other part that is somewhat confusing to me is how we like this workhorse tool, and then we try and use it in almost the same way towards all problems, rather than taking advantage of things like large deviation theory to try and accelerate for extreme events, or emulators to try and fill out the probability distributions and the internal variability, rather than using multi-model ensembles, which are really inefficient at that same effect. And so I guess, I think we have a really good tool, but we should be branching out from that in a lot of different directions all at the same time, and seeing what flowers from that, rather than trying to decide as a community that, what's the one new tool that we are all excited about using next time around. That is a difficult thing to ask a community to agree to do, to agree not to agree. But I feel like, there are many more good ideas than we have need for models.
And I think this is a very important point. It comes back to some extent, at least, to what Daniela was alluding to or addressing. And also thinking kind of what's actually the role of WCRP, maybe in fact to some extent to write this little recipe book, what should be done with all the knowledge, all the theories, everything that's there that we usually do not know all about. But maybe in fact we should bring in together this little group writing this assessment of how we should use what we have, and maybe still identify what's missing, but that we all get clearer on the benefits we have, and maybe the few points that the few niches where we really need to have development. But I think that's in some sense WCRP as a coordinating body. Maybe this is exactly what we should put on our list, what we should do. And with this, maybe we do come now to Nico's group photo, and we all go into the staircase, I guess, and in Geneva.
I became the official photographer, so please, everybody, just put your cameras on. I will stop the YouTube while you do this. We are going to stop this YouTube stream. So for those watching on YouTube, you are welcome back tomorrow at the same time. So thanks